Section 10.4, the ideal gas equation. In Section 10.3, we examine three historically important gas laws that describe the relationships between the four variables, pressure, volume, temperature, and number of moles, that define the state of a gas. Each law was obtained by holding two variables constant to see how the remaining two variables affect each other. We can express each law as a proportionality relationship using the simple proportion, which is read proportional to. We have Boyle's law, volume is proportional to 1 over the pressure, constant and number of moles, temperature and number of moles constant. Charles's law, the volume is proportional to the temperature, the number of moles and the pressure are constant. And Avogadro's law, the volume is proportional to the number of moles, with pressure and temperature constant. We can combine these relationships to make a more general gas law. Volume is proportional to the product of number of moles times the temperature divided by the pressure. If we call the proportionality constant R, we obtain V equals R NT over P. Rearranging, we have this relationship in its more familiar form. PV equals nRT. This equation is known as the ideal gas equation. An ideal gas is a hypothetical gas whose pressure, volume, and temperature behavior are described completely by the ideal gas equation. The term R in the ideal gas equation is called the gas constant. The value and units of R depend upon the units of P, V, and N, and T. Temperature must always be expressed as an absolute temperature when used in the ideal gas equation. The quantity gas N is normally expressed in moles. The units chosen for pressure and volume are most often atmospheres and liters, respectively. However, other units can be used. In most countries other than the United States, the SI unit of Pascal is most commonly employed. Table 10.2 shows the numerical value for R in the various units. As we saw in the closer look box on PV work in Section 5.3, the product of pressure volume has the units of energy. Therefore, the units of R can include joules or calories. In working problems with the ideal gas equation, the units of pressure, volume, moles, and temperature must agree with the units in the gas constant. In this chapter, we will most often use the value of R equals 0.08206 liter atmospheres Kelvin moles, 4 significant figures, or 0.0821 liter atmospheres moles Kelvin, 3 significant figures, whenever we use the ideal gas equation, consistent with the units of atmosphere for the pressure. Use of R equals 8.314 joule mole Kelvin is consistent with the units of Pascal for pressure is also very common. Suppose that we have 1 mole of an ideal gas at 1 atmosphere and 0 Kelvin, or 0 degrees Celsius, 273.15 Kelvin. According to the ideal gas equation, the volume of the gas is 22.41 liters. The conditions of 0 Celsius and 1 atmosphere are referred to as standard temperature and pressure, STP. Many properties of gases are tabulated for these conditions. The volume occupied by 1 mole of ideal gas at STP, 22.41 liters, is known as the molar volume of an ideal gas at STP. The ideal gas equation accounts adequately for the properties of most gases under a wide variety of circumstances. The equation is not exactly correct, however, for any real gas. Thus, the measured volume V for given conditions P, N, and T might differ from the volume calculated from PV equals nRT. To illustrate, the measured molar volumes of real gases at STP are compared with the calculated volume of an ideal gas in Figure 10.13. While these real gases do not match the ideal gas behavior exactly, the differences are so small that we can ignore them for all but the most accurate work. We will have more to say about the differences between ideal and real gases in Section 10.9. Figure 10.13, comparison of molar volumes at STP. 1 mole of ideal gas at STP occupies a volume of 22.41 liters. 1 mole of the various gases at STP occupies close to this ideal volume. Relating the ideal gas equation and the gas laws. The simple gas laws that we discuss in Section 10.3, such as Boyle's law, are special cases of the ideal gas equation. For example, when a quantity of gas and the temperature are held constant, number of moles and temperature have fixed values. Therefore, the product, nRT, is the product of three constants and itself must be a constant. Thus, we have Boyle's law. We see that if n and t are constant, the individual values of p and v can change, but the product, pv, would remain constant. We can use Boyle's law to determine how the volume of a gas changes when the pressure changes. For example, if a metal cylinder holds 50 liters of oxygen at 18 atmospheres and 21 Celsius, what volume would the gas occupy if the temperature were maintained at 21 Celsius while pressure and reduced to 1 atmosphere? Because product PV is a constant when a gas is held at a constant number of moles in temperature, we knew that P1V1 equals P2V2. Where P1 and V1 are initial values, P2 and V2 are final values. Dividing both sides of the equation by P2 gives the final volume, V2. Substituting the given quantities into this equation gives you V2 equals 925 liters. The answer is reasonable because gases expand as their pressures are decreased. In a similar way, we can start with the ideal gas equation and derive relationships between any two variables, V and T, Charles's law, N and V, Avogadro's law, or P and T. Sample exercise 10.5 illustrates how these relationships can be derived and used. We are often faced with a situation in which pressure, volume, and temperature all change for a fixed number of moles of gas. Because N is constant under these circumstances, the ideal gas equation gives PV equals over T equals NR, which is a constant. If we represent the initial and final conditions of pressure, temperature, and volume by subscripts 1 and 2, respectively, we can write P1V1 over T1 equals P2V2 over T2. This equation is often called the combined gas law.